So today we need to talk about some design patterns which usually are used in deep learning. I will share also the link with you for the streaming. So you can share it with other people who cannot attend today, for example, or if you want to go back to the lecture. So it's advanced CNN architectures. So first we need to talk about CNN design patterns. Pattern one is feature extraction and classification, which we know. So our model will consist of two parts. The first part will consist of feature extraction, and the second part is classification. This is the traditional part, right? This is the traditional way for building CNN model. So it consists of two sections or two parts. The first part, it's about feature extraction, and the second part is about classification. The feature extraction will try to extract features which make sense for our problem, and after that we will have a classifier, and this classifier will do classification or regression or whatever. Pattern number two, its image depth increases and the dimension decreases. So it's also, we can control this, of course, this pattern two. So where image depth increases and the dimension decreases of the image, so height and width decreases, but depth increases. Pattern number three, it's fully connected layers. So also we need to understand some advanced architectures like LeNet, AlexNet, BGGNet, for example, Inception model, which is a CNN model with some inception modules, and ResNet, for example. But I mean, the door is open for more models. There are lots of models which you need to explore, for example. And I mean, the selection is based on your problem, of course. So pattern number one, each feature extraction and classification. We know this one, right? If we need to build a CNN model, first we need to extract features. So the first part of our model will consist of number of conv layers, and conv layers followed of maybe max pooling and so on. But anyway, the first part, it's about feature extraction. So we need to feed this one with the raw data, right? We have here raw data. And this feature extraction part, it will consist of number of conv layers. And at the end here, we will have some features, high-level features. And once we have those features, we will feed it to a classifier. And the classifier will consist of a number of fully connected layers. And fully connected layers, it's traditional machine learning model, just fully connected layers, right? And the last layer here, this one, it will be used for classification. So if you are working with multi-class classification, maybe you can select here, we can call the last layer soft max layer, because we can use here an activation function which will calculate the probability. So it composed of two parts: feature extraction, which consists of a series of convolutional layers, and the classification part, which consists of a series of fully connected layers. So this structure is very, very simple, and it's very traditional structure. In pattern two, image depth increases and the dimension decreases. The dimension, we mean by dimension is height and width. So the height and width of the image, it will decrease over time. So as you can see here in this structure, for example, we are starting from 224 times 224, and we ended with 13 times 13, which means the spatial dimension decreases while depth increases. I mean, the depth here in the input image, it's a 3, correct? Because it's RGB image. So the RGB image, it has 3 channels. So we have here the height is 224 pixels. Width is 224 pixels multiplied by 3, right? Why 3? Because the input image here, it's RGB image. It could be also 1 if it is gray scale image. So, and after that, we will apply some conv layers. So we will apply some filters. We will apply some, so this is the output from the, from the conv layer. And after that, it will be followed by a max pooling layer, and it will be converted into this one, right? As you can, if you can remember, I mean, max pooling, it's according to the stride, right? We reduced the dimension, a special dimension from 55 times 55 to 27 times 27 because it reduces, it do some downsampling, and it reduces the dimension from its full scale into maybe quarter. So it will be 27 times 27, which means we reduced the spatial dimension by maybe 75%, right? So maybe applying another conv layer, another conv layer to this one, and followed by max pooling layer, it will be converted back again. It will be reduced back again to 13 times 13, which means we reduced also the dimension again by 75%. But the depth increases, as you can see. So we are starting with 224 times 224. We ended by 13 times 13 times 384, correct? So it's according to the selection of filters and the use of max pooling layers. We try to reduce the dimension of the input image and increasing the depth. So the input data at each layer is an image. At each layer, we apply a new convolutional layer over a new image. Each image is a 3D object that has a height, width, and depth, correct? But in each layer, I mean the height and width, it will reduces and the depth will increases. So the output from the first conv layer, it will be 55 times the 55 times 96, because we selected 96 filters, right? So when you are selecting 96 filters, the depth will increases to 96. And special dimension, it will go down to 55 times 55 because you selected a filter size here of 11 times 11, of course times 3 because the input image is RGB image. So it will go down into 55 times 55. After that, you will select a max pooling layer. The kernel here is 5 times 5. So it will reduce the dimension to 27 times 27. This one also, it will be based, I mean, the depth increases from 96 to 256, and it's based also on the number of filters which you are selecting. So, so the depth is referred as a color channel. So the color channel will go down from 3 into 96 into 256 into 384, right? And so on. Depth is 1. Depth is 1 for grayscale image, and it's a 3 for color image. And for the inner layers, it will be the number of filters, right? So the input image here has 3. The number of channels equals 3 because it's RGB image, but also it could be 1 also if your image is a grayscale, like MNIST dataset. MNIST dataset, it's a grayscale, which means it has only 1 channel. The color depth is 1, or the number of colors is only 1. But when it is RGB image, for example, number of channels will be 3. In later layers, the image will have depth, but they are not colors, they are feature maps. I mean, the depth here, it's not color, but number of filters or number of features, right? In this pattern, the image depth increases and the dimension decreases. So this is one of the famous design patterns which are used. Pattern number 3, it's fully connected layers, and this fully connected layers it's just a traditional machine learning models, and it's very similar when you designed a model for classifying MNIST dataset. You just use the fully connected layers, right? We don't have any feature extraction. So in this case, we will be working on the pixel level, right? We will not extract any features. I'm talking about MNIST dataset. So in this case, we will just build a model which will consist of a number of fully connected layers. That could be 2, 3, for example, and so on. So all fully connected layers in a network either have the same number of hidden units or decreases at each layer. So you can start with, for example, the input, because imagine that you are working with MNIST dataset, and the image of MNIST dataset is 28 times 28 pixel values. So the number of, if we are working with pixel values, it will be number of inputs will be 28 times 28, so it will be 784. 784. So number of input will be 784. So we're expecting that the first fully connected layers maybe to have maybe, for example, whatever, any number, But in the output layer, we need to classify into 10. So this is the output layer. So we need to classify into 10 classes. So in this case, we need to go from 708. So if we can just say that number of inputs here will be from 1 to until 784. So we need to go from this number into 10. So usually people go into the direction. So usually people prefer to have it like this one. So we will have, imagine that we will have 3 layers. So we will have the input layer, first hidden layer, second hidden layer, output layer. So if you are selecting number of nodes here, for example, 600, so should expect is that this one, it could be less. So it could be, for example, 250. If you need to use another layer here, it could be, for example, maybe 50 or 100. And after that, we will go. So we need to go gradually from this number into 10. So just 1 second, please. Yes. So sorry for interrupting you. So this is the pattern number 3, which is fully connected layer, which is very traditional. So all fully connected layers in a network either have the same number of hidden units or decrease at each layer. So usually people prefer to just decrease because we need to go from 784 pixel values into 10 classes. So usually people prefer to go into that direction. So it's rare to find a network where the number of units in the fully connected layers increases at each layer. It's difficult, in fact, but in fact, a long time ago, people used to go from the input size to number, large number, and after that go down into like this one. But this is very, very rare to see this kind of pattern, because in this case, I can go from, imagine that I will go from 10, for example, to 20, and after that to 10 classes, for example. It could be something like this one. So after that, we need to start with some famous neural network models or CNN models, and we need to start with LeNet 5. LeNet 5. And LeNet 5, in fact, it was named by the author of this model. His name is Lee Kon et al. It was introduced in 1998 by this person, Lee Kon et al. And in fact, they call it LeNet. So Lee comes from his first name, right? Lee, and the net because it's a network, right? And the 5 because it consists of 5 layers. This model consists of 5 weighted layers. So the architecture is composed of 5 weighted layers. and therefore they call it LeeNet 5. So you know the name, I mean, from where it comes. So it was introduced for the first time in 1998. Lee, it's the first, I mean, those first two letters, it's because his name is Lee Kun. So it's his first name, Lee, or last name, I guess. Net, because it's network, and 5 because it consists of 5 layers. Those 5 layers are 3 conv layers and 2 fully connected layers. So we will go back again to the first architecture, which we studied today. The feature extraction part will consist of 3 conv layers, and the classification part will consist of 2 fully connected layers. So the design is very simple. The architecture is very, very simple. So LeeNet 5 consists of 5 layers. Those 5 layers are 3 conv layers and the 2 fully connected layers. 3 conv layers for feature extraction. So as you can see here, with MNIST dataset, I mean, it has been trained and tested using MNIST. So the input image is 28 times 28 pixel values, right? And this one, it's a grayscale, which means it's one channel. So I can say that we will multiply it by 1, right? Because it's only one channel, it's a grayscale image. So we will feed this image to the first conv layer. So the first conv layer, it will try to extract, as you can see here, 6 features. Do you see? So the depth will go up from 1 to 6 because the input image has one channel, and the first conv layer, it will extract 6 feature maps. 6 feature maps. And those feature maps will have the same size, 28 times 28, which means the dimension of the image will not decrease. And why it will not decrease? Because we used zero padding, if you can remember. Do you remember zero padding? So zero padding, we would select it as same. I mean, you know, when we are selecting zero padding, it should be same or void. Void means we don't have any zero padding, and the same means we will use zero padding in order to keep the image dimension the same, right? So the image dimension will stay the same. It will be 28 times 28, which means we use the zero padding, and number of channels will increase from 1 to 6. Why from 1 to 6? Because in the first conv layers, we selected 6 filters. Each filter will select a feature map. So in this case, we will have 6 feature maps. In the input image, the input image has only one channel because it's a grayscale. So the number of colors is 1. We have only one color, correct? But the feature maps, which will be extracted from the first conv layer, will be 6. We cannot call it 6 colors, but the depth equals 6 because we have 6 different feature maps. So this is the first conv layer. This conv layer, it will be followed by subsampling layer. This subsampling layer, it's pooling layer, right? It will be followed by a pooling layer. This pooling layer, it will reduces the dimension of each feature map from 28 times 28 to 14 times 14, which means it's a quarter, right? So if this one is, I will draw it here. If it is 28 times 28, now we will reduce it into 14s times 14s, which is just quarter, which means we reduce the dimension by, it's 50%, correct? But in fact, we did this subsampling, we reduced the dimension of the whole, the input image by maybe 75%, as you can see, because it's 25% of the total size, right? So again, the first conv layer has 6 filters, so it will extract 6 feature maps. The feature map, each feature map will have a size of 28 times 28, which is the same size of the input image. And this is because we use the zero padding, and when we are use zero padding, we will keep the same dimension. We will keep the same height and width. So now we got 6 feature maps of 28 times 28. This layer, it will be followed by a pooling layer. This pooling layer, it will reduces the dimension from 28 times 28 into 14 times 14, but the number of feature maps will stay the same. right? The input layer, this conv layer has 6 filters, correct? So and the pooling layer, it will have only one kernel, right? I don't know the size, maybe it's 2 times 2, which will reduce the dimension from 28 times 28 to 14 times 14. So anyway, after this layer, we have 6 feature maps, which has a size of 14 times 14. We will apply another. So this is the first conv layer. We will apply another conv layer. We will apply another conv layer. This conv layer, it will, we didn't use zero padding, correct? We didn't use zero padding, so, and therefore the size of each feature map, it will go down from 14 times 14 to 10 times 10. Just look into those numbers. So now the dimension will go down from 14 times 14 to 10 times 10, because we didn't use here zero padding or zero padding equal 1, right? Number of feature maps, it will go up to 16, which means the depth will increases. So as you can see here, the depth here was 1, the depth here is 6. So the depth here will increases, it will become 16, which means in the second conv layer, we selected 16 feature maps, right? We selected 16 filters, and each filter, it will extract a feature map from the input volume, which is 14 times 14 times 6, right? So in this case, we will have 16 feature maps. The size of each feature map, it will be 10 times 10. So this is a second pattern. Do you remember the second pattern? Where the image dimension will go down, but the depth will increases. This one will be followed by subsampling again. This subsampling, it will reduces this one to half, from 10 to 5, and this one from 10 to 5. We will keep the same feature maps, 16, correct? So the output volume now, it will be 5 times 5 times 16. Before applying this one, okay, average pooling. So this is another visualization of it. So we have here the input image. We will apply conv layer. The filter size is 5 times 5 stride equal 1. We didn't use zero padding, so we will get this volume. After that, we will apply average pooling. Average pooling of 2 times 2, the filter size will be 2 times 2, stride equal 2. So it will reduce the dimension from 28 times 28 to 14 times 14. We will apply another conv layer of filter size 5 times 5, stride equal 1. So it will produce 16 feature maps. Each has a size of 10 times 10. It will be followed by average pooling. This average pooling has a filter size 2 times 2, stride equal 2. So it will reduce the dimension from 10 times 10 into 5 times 9, and we will keep the same number of feature maps. So at the end, we will have, how many pixels we will get? It will be 5 times 5 times 16, which is 120. So if you want to check this number, so it will be 5 times 5 times 16, which is 100. I guess we still have here conv layer. So we have another conv layer after this one, right? We have here another conv layer. So this is the first conv layer, second conv layer. This is a third conv layer. So we will apply another conv layer to this one, and it will produce 120 pixel values, or a feature map, which will be flattened. When it is flattened, it will produce 120 values, right? So we will have those numbers. We call this one flatten layer, right? We call it flatten layer. We will have two fully connected layers. This is first conv layer. This is a fully connected layer, and this is fully connected layer 1, fully connected layer 2, for example. So anyway, we will do flatten after this conv layer. We will get 120 values. those 120 values will be applied to the first fully connected layer. The size of the first fully connected layer is 84. And the output layer has 10 because it's MNIST dataset. We need to classify it into one of 10 classes. So in that model in 1998, they used hyperbolic tangent as an activation function. At that time, they don't have, in fact, I mean, at that time, 1998, we didn't have rectified linear unit at that time, has not been used at that time in deep learning. So they used the hyperbolic tangent as an activation function instead of the state-of-the-art rectified linear unit. At the time, we didn't have rectified linear unit, so they used hyperbolic tangent as an activation function. And of course, I mean, when we compare hyperbolic tangent function with rectified linear unit, we know that this one has a problem with vanishing gradient. So this hyperbolic tangent is very bad, in fact, with respect to vanishing gradient. So it does not have a good performance, and therefore, I mean, it's not very deep model. It consists only of 5 layers, three conv layers and 2 fully connected layers. They cannot go deep because when they go deep, maybe the model will not be able to learn. Why? Because of the vanishing gradient problem. Vanishing gradient problem, right? So if we need to train this model for MNIST, I have here an example. I need to open this example and share it with you in the chat so you can open it and try to play with it. So we have here the link. And I will share my code in Google Colab. So we can build our model and train our model using. So you have the link, please. I will share another screen. So as you can see here, I will open it in Google Colab. So we need to, I mean, to build your model, you need to, first you need to load your data, which is MNIST dataset. So as you can see here, we will load it from keras.datasets.mnist. We need to get our dataset here. We need to use this function toCategory again, because when we are loading our data,
I think it stops sharing your screen.
You don't see my screen?
I can't. I don't know how others.
Okay, maybe I will. Okay. Can you see it now?
Yeah, I can.
Okay. Yes. So this is my. I mean, this line, as you can see here, this line we try to load our data. So we need to load MNIST. We will get it from keras.datasets. This function is very important because the target feature here of this dataset, it will be one column, and this one column will contains the category, which is a number between 0 and 9. So we need to convert it into 10 values. So we need to use one hot encoding. So this function, it will provide us with this 10 one hot encoding. So we can convert this column into 10 values, not only one column. It will be converted into 10 column, and it will contain 1 at the index of that category and zeros otherwise. We need to build our model, so we will use sequential API, right? I mean, last week or the week before the new year, we used sequential and the model. We use the sequential API for building our own model, and also you can use model API when we try to build a submodel for showing the intermediate values. If you can remember from last lecture, we try to see the intermediate values or some feature maps. I want to display the feature maps from some conv layers, for example. So in this case, you need to build a submodel which will start from the input and it will end up at that layer. where you want to display the feature maps. We need to import layers from keras.layers. We need to import conv2d, for example, average pooling, flatten layer, and the dense layer. Dense layer, it is a fully connected layer. Flatten layer, it's very important because it will combine the extracted feature maps and it will convert it into 1D vector, which will be suitable for providing inputs to the dense layers or the fully connected layers. And we know average pooling is very important. Average pooling and conv layer, usually the feature extraction part, it will consist of a number of conv layers followed by average pooling layers. And of course, here we need to get confusion matrix and other evaluation metrics. We need to import it from sklearn.metrics. We would run that part first. So after that, we need to load our data. So as you can see here, the original dimension, it will be 60,000 times 28 times 28. So this is the input features, correct? So it's X. This one, it's about X. So the original dimension, xtrain.shape, it will be 60,000 times 28 times 28. It's a grayscale. So it's 28 times 28 times 1. For this one, for xtrain, for xtest, it will be the same, but it will be 10,000, not 60. So we use 60,000 for training and 10,000 for testing. And ytrain here, it will consist of two values, one column, which contains 10 values from 0 to 9. But we use this function toCategorical, which will do some one-hot encoding. So in this case, we will convert it from its original dimension, which is 1D vector, into 10, right? So the size of this one, I mean, the original size of ytrain, it will be one column. In fact, it will be only one column. But when we are using this function toCategorical, we will convert it from one column into 10 column. And those 10 columns, it will be one at the index of the image and the zeros otherwise. We need to build our model. So we need to build this LeNet model. So as we agreed that in LeNet model, it consists of 3 conv layers, right? So we will use sequential API to build it. And it will consist of 3 conv layers followed by 2 fully connected layers, right? So as you can see here, we will use the first conv layer. So the first conv layer, it will consist of 6 filters, right? The kernel size is 5, which means it will be 5 times 5, right? Stride equal 1. The activation function is hyperbolic tangent. The input shape, it will be 28 times 28 times 1, which is the input, which is the size of the input image. It's a grayscale, so it will be 28 times 28 times 1. We will use padding equal same, which means we will use 0 padding. And in this case, it will produce, what will be the size of the output when we use padding equal same? It will be the same as the input size. So if the input size is 28 times 28, the dimension also of the output from this conv layer, it will be 28 times 28. But the dimension will increase because the input dimension here is 1, but we selected number of filters equal 6, which means each filter will extract a feature map. So in this case, the depth will go up from 1 to 6, right? Because we select number of filters equal 6. So we should expect that the output from this layer here, output shape, when we use model.summary, it will give us this table. So as you can see here, the output shape, it will be 28 times 28 times 6. Why? Because we use the padding equal same and the number of filters equal 6. Each filter, it will extract a feature map. So we should expect that we will get here 28 times 28 times 6. So after that, we will use average pooling layer. Average pooling layer, it's average pooling layer. It will do this down sampling, correct? Down sampling. So it will reduce the dimension because we have stride equal to the pool size equal 2, right? So So the filter here will be 2 times 2 with stride equal 2. And when we use this combination, we will reduce the dimension from 28 times 28 into 14 times 14. Number feature maps will be the same. It will not change after average pooling, but only the dimension, which is the height and width. So it will be 14 times 14. If we need to check here number of parameters, here it's 156. Why it's 156? Because number of filters equal 6, and the kernel size is 5. So should expect that number of parameters will be 5 times 5 times 6 plus 6. If you can remember from last time, each filter will be a perceptron, and each perceptron has a bias. So if you want to calculate number of parameters here, it should be 5 times 5 times 6 plus 6. We should get this number. So I will test it with my phone. So it will be 5 times 5 times 6 plus 6. So it will be 156. This is correct. So average pooling layer, it does not have any parameters. It will just do a kind of downsampling. So number of parameters here will be 0. After that, we will go to the second conv layer, right? And as you can see, padding equal valid, which means we will not have a 0 padding here. Activation is a hyperbolic tangent. It's not the best choice, but this is a choice which was available in 1998. The kernel size equal 5, which means this one, it's a square, right? So it will be 5 times 5, but number of filters equals 16, correct? So in this case, we should expect that the output from this layer, it will be 16 feature maps. As you can see here, yes, we have 16 feature maps. But because we didn't use 0 padding, the dimension will go down from 14 times 14 to 10 times 10. But the depth will increases because the depth becomes 16 because we selected here 16 filters. If we need to calculate number of parameters here, can you calculate this number, please? Can you get this number here, number of parameters? Can you try to find this number? Yes. Can you calculate? Can you find number of parameters? The second conv layer, which is 2416. 2416. How can we get this number? We have here in this layer, in fact, we have 16 filters. So it will be 16 times what is the filter size? It's 5 times 5. So it's 5 times 5. What is the depth? It's the depth of the input. So the input is 6 plus bias, which is 16. So it should be, this number should give us that number. So I need to test it. So it should be 16 times 5 times 5 times 6 plus 16. 2416. Yeah, so I got it here in my phone. So it's 2416, as you can see here, right? Yes. So this conv layer, it will be followed by another average pooling layer. So in this average pooling layer, the filter size will be 2. So it will be 2 times 2 with a stride equal 2, which means it will reduces also the dimension and not the depth from 10 to 5, right? So we will go from 10 to 5. So now after downsampling, the feature maps will have a size of 5 times 5 times 16, correct? After that, we will go to the third conv layer. Number of filters here, it will be 120. Kernel size, it will be 5 times 5. And as you can see here, if the input image is 5 times 5, and you will apply a kernel which has a size of 5 times 5, you will apply it only one time, correct? So in this case, in fact, we will apply each filter. We will have 120 filters. And the filter size is 5 times 5. and the input image or the input feature map has a size of 5 times 5, correct? So in fact, you a stride equal 1, but you will not use a stride because you will just apply, you will apply the filter one time, you will do activation only one time, and that is it. And of course, from this one, you will get only, when we apply this filter, you will get only one pixel value or one value, because when you apply the filter, which has a size of 5 times 5, to an input image which has a size of 5 times 5, you will do your calculation, you will get only one activation, so you will get only one value. So in fact, the output from this one, it will be 120 values. And the input image or the feature map will be 1 times 1, as you can see here. So it's 1 times 1 times 100. Why? Because the kernel size is 5, which means it will be 5 times 5. And the input feature map, it's 5 times 5 times 16, correct? So when you apply this feature, the kernel, to the input features, it will be applied only one time. We will not move, right? So we will do one activation, and we will get this number. So the output from this one, it will be 120 times 1 times, sorry, it will be 1 times 1 times 120, right? So in this case, there is no need, in fact, to use downsampling after this layer, because anyway, each feature map has a size of 1 times 1, correct? Each feature has a size of 1 times 1, so there is no need, in fact, to apply another average pooling after this one. You cannot apply it anyway. So the output from this conv layer, it will be 1 times 1 times 120. Number of parameters of this layer, can you calculate this number? This one? It's 48,120 parameters. So to get this number, we need to go back to our conv layer, which has 120 filters, and each filter has a size of 5 times 5. But because the input feature map has a depth of 16, right? So should expect that number of parameters here, it will be 120 multiplied by 5 times 5 times 16 plus 120 to get this number, right? To get this number, right? After that, it will be followed by a flatten layer, right? Because we need to flatten it, we need to convert this one into 1D vector. So the input will be 1 times 1 times 120. When we flatten it, it will be converted into a vector of 120 values, right? It will be 120 values. It will be 1D vector of size 120. Once you have this number of features, correct, you will apply it to the fully connected layer. In this model, so this model, it consists of feature extraction part, which is that part, and the classification part, which is that part, right? So this is a design pattern. So the first part, it will be about feature extraction, and the second part, it will be about classification. So the classifier will consist of two layers. The first layer has 84 units, neurons, with an activation of hyperbolic tangent. And the output layer, it will consist of 10 units, because we need to classify each image into one of those 10 classes. And the activation here, it will be softmax. Why we are selecting softmax? Because we calculate the probability of each image belonging to one class. So we'll use softmax layer. When you are using softmax layer in this layer, usually people call it softmax layer, right? So usually people call this output layer a softmax layer because we used a softmax activation function. So we will apply those 120 values to this layer. So if we need to calculate number of parameters here, how can we calculate this number? It should be 84 times 120 plus 84. We will get this number. And for the output layer, number of outputs from this layer, it will be 84 because we selected 84 units or neurons, and each neuron will produce one value. So should expect is that the output shape will be 84. So 84 values, it will be applied to the output layer. So number of parameters here, it should be 10 multiplied by this number plus 10. We will get this number 850. So this is my model. And if we continue looking into these numbers, so this is the total number of parameters. It will be 61,706. And this number, in fact, is a summation of those numbers. So this number plus this one, plus this one, plus, you will get this number. We have also something else. We can divide the total number of parameters into trainable and non-trainable parameters. And as you can see, all parameters here are trainable, which means we need to train all those models. Non-trainable parameters equal 0 because we are not using the transfer learning, right? If we are using a transfer learning, in this case, we will get trainable and non-trainable parameters. So we will run that part. So we are building our model. Now we have our model. We will compile it. We will select loss function categorical cross entropy. We will use SGD as optimizer, and evaluation metrics, it will be accuracy. And after that, after compiling your model, you need to fit your model or train your model using XTrain, YTrain. Batch size equals 32. We will train the model for 20 epochs. And the validation set will be, I used here the test set for validation, right? Which is not correct. So we use the X-test, Y-test for validation. Of course, we should not use this, right? We should use part from the training data for validation, and we need to keep the X-test and Y-test for testing your model. As you can see here, I mean, the loss is decreasing. It goes down from 0.6. Now it goes down. The accuracy also, it goes up from 83% to 96% in 7 epochs. This is the validation accuracy also. So from this history, from this one, we should be able to plot the training and training, validation, loss, and accuracy, because those figures are very important, or graphs are very important, because it will help you to see if your model is overfitting your data. So, training now is done. We reached epoch number 20. Yes, now it's finished. So now I need to print maybe some average values of loss. Training loss, training accuracy, validation loss, and validation accuracy. So I can do it here. We can do some predictions, calculate scores, and also plotting training loss against the validation loss, and the training accuracy against the validation accuracy. As you can see here, we got those numbers here. So training and validation loss, it's those numbers, training and validation accuracy, right? Training and validation loss, and this is training and validation accuracy. As you can see here, the training accuracy was 96%, and for the validation set, it was 97%. And we have those graphs here. I mean, this one is for the loss, training loss and validation loss. As you can see here, loss, I mean, for the training loss, it will go down all time. And also for the validation, it started from some point, random point, and it will go down. And maybe if also we will keep training the model, we will enhance the performance. We trained the model only for 20 epochs, and this is the training and validation accuracy, and both of them are increasing. You can see that the model is not overfitting, right? Also, if you want to get the confusion matrix, because from those numbers, it's just for the whole model. And those numbers are representing the whole model accuracy. But if you want to see the performance of the model for each individual class, so in this case, you need to have the confusion matrix. So we will run that part. We'll get the confusion matrix here. As you can see here, for class number 0, for example, 970 zeros classified as 0, right? So this is a predicted label on the x-axis, and in the y-axis we have true labels, which means here, and if we need to read the first number here, 970, it means 970 zeros were correctly classified as zeros. But we have 1 0 classified as 4, we have 4 zeros classified as 6, we have 3 zeros classified as 7, and 1 0 classified as 8, and 1 0 classified as 9. So as you can see here, the performance is very good for the test set. But just remember, we did that for the test set. Yeah. I mean, we did that for y-predict. I mean, we got y-predict for x test, right? For the test set. And we can plot the confusion matrix for y-predict and y-test, right? But just remember that we used here the test set for validation. We should not do this, right? We should not do this. So here you can see the performance of the model against each class, for example. And maybe we have, the performance is very good, in fact, for this, our first convolutional neural network with MNIST dataset. So I hope that you can go to this to the link and try to play with this example. So I will go back again to our slides. So as you can see here, if you can see my screen, I guess you can see it, right?
Yes.
Okay.
Visible.
Yeah, so this is our model. So the model consists, as we mentioned, the model consists of 5 layers, 3 conv layers and 2 fully connected layers, right? And the model is very simple. And in 1998, they used the hyperbolic tangent because at the time we didn't have rectified linear units. So in fact, you can repeat this example and try to change the activation function from hyperbolic tangent into rectified linear unit and try to see what is the difference. Is there any difference? Can we get better accuracy if we just change it? I mean, we will train the model for 20 epoch. We will not change anything. We will just change the activation function from hyperbolic tangent into rectified linear unit, and we will see the performance. Is there any improvement in the performance? We should see some improvement because the rectified linear unit should perform better against vanishing gradient. And at the time, in fact, they didn't go deep, and the model is not very deep. It has only 5 layers. Only 5 layers, because they used hyperbolic tangent. Maybe if you will increase the depth, if you will make it 6, 7, 8, using the same activation function, you will have a vanishing gradient problem, and the model performance will be bad, will not be good. Why? Because we're using hyperbolic tangent, and hyperbolic tangent is not performing very well against vanishing gradient. So if you want to test this vanishing gradient problem, try to increase the model depth, add one more dense layer, fully connected layer, for example, or 2, and I try to also increase the depth of this feature extraction part, add more conv layers, for example. So try to make some modifications and try to increase the model depth, right? and use the same hyperbolic tangent activation function, and you see the performance, we should expect that the performance will be worse. And also try to replace the hyperbolic tangent with rectified linear unit, and try to train your model, and you see the difference. We should expect that with rectified linear unit, we should get better performance. So the model should be trained in a less number of epochs. We should achieve better accuracy. So this is the confusion matrix, and this is a table which we just explained. This is the accuracy will be 98%, 98.7%. This is the overall accuracy, but of course you can get the accuracy for each class, right? Okay. I guess we will stop here, and we will give you maybe 10 minutes break, and after that we will start in the second part. Yes, thank you.
So 10:30.
Yes, okay. Yeah,
Okay.
thank you. Bye-bye.